Let's get ready for the Unit 5 quiz. Number 1, solid iron has a specific heat of 0.45 joules per gram degrees Celsius. What that means is it takes 0.45 joules to heat up 1 gram of iron 1 degree Celsius. Benzene, on the other hand, has a specific heat of 1.74 joules per 1 gram degrees Celsius. That means it takes over 3 times as much energy, 1.74 joules, to heat up 1 gram of liquid benzene 1 degrees Celsius. So the question here is, what if you had 10 grams of iron and 10 grams of benzene? You add the exact same amount of heat to each sample. Which one is going to heat up more? Well, it would be iron. Why? It takes only 0.45 joules versus 1.74 joules to heat 1 gram up 1 degree Celsius. So iron is going to have a much greater change in temperature. Number 2, how much energy does it take 50 grams of ice to go from negative 25 degrees to a liquid at 75 degrees Celsius? Let's go off to the side and sketch a little energy heating diagram. So we're starting at negative 25. When it heats up, something special for H2O happens at 0 degrees. It melts. Then this problem asked us to continue to calculate how much energy it takes to get up to 75 degrees Celsius. So here we've got a solid, here it's melting, and here is a liquid. That means we need 3 different equations. I'm going to call this A, B, and C. So first for letter A, we're going from negative 25 up to 0 degrees Celsius. That's when H2O is in its solid form, it's ice. To calculate the energy it takes, we're going to use Q equals mc delta T. Let's review what these letters stand for. Q is how much energy it takes. M is mass, which for this question is 50 grams. C is specific heat, and there's a table of all the specific heats that you will have access to. So you look at the specific heat for water when it's in its solid phase is 2.06. That means it takes 2.06 joules to heat 1 gram 1 degree Celsius. Finally, multiply by the change in temperature. So we're going from negative 25 to 0. That's a change in temperature of 25 degrees Celsius. Multiply those together and you get 2,575 joules. Notice grams cancels out, degrees Celsius cancels out, and we're left with joules. Okay, so that's just one step right here. Step A. How about step B? We're going from 0 degrees Celsius solid up to 0 degrees Celsius liquid. We're not changing temperature, so we can't use the same formula. We need to use the melting formula, which is the heat of fusion times how many moles you're trying to melt. Again, the heat of fusion is just a constant that's given to you for each of the substances, and for water it's 6,010. So that means it takes 6,010 joules to melt 1 mole of water. So I'm going to put in 6,010 joules per mole. Oh no, we've got 50 grams of ice. We got to figure out how many moles that is. So I'm going to go down here, 50 grams of H2O. How many moles is that? Well, 1 mole of H2O is equal to 18.02 grams. So we definitely have more than a mole. We've got 2.77 moles. So how much energy is it going to take to melt this 50 grams? 16,647.7 joules for step B. We still have step C. How about going from 0 degrees Celsius as a liquid up to 75 degrees Celsius liquid, like the problem asks us to do? Again, we need to use Q equals MCAT, but this time we use the specific heat for water in its liquid phase. We've still got 50 grams of water, but now if you check your chart, the specific heat for H2O in its liquid phase is 4.18 joules per gram degree Celsius. And the temperature change from 0 to 75 degrees is 75. Multiply those together and it comes out to be 15,675 joules. Now, with these three numbers that I have circled, I need to add them all together to find the total energy. So I did that and it came out to be 30. So where'd you go, 3? There's some sort of a delay on this. Let's see here. Come on, computer. 34,897.7 joules. Final answer. And again, if you rounded that a little bit differently, that's totally fine. That's going to happen. That's why you need to show your work. Moving on. Number 3. Here's a little table that tells us what's going on when butane is combusting. This is very much like your burning foods lab. So imagine you've got a can of water, and according to this problem there are 500 grams of water in this can. The temperature of the water went up from 25 degrees up to 55 degrees Celsius because there's a fire underneath, and you're not burning a Cheeto, you're burning butane gas, which has, it's actually a liquid, sorry, the formula C4H10. Okay, but you're going to do this problem in the same way that you did your combustion of food lab. So first, how much energy was absorbed by the water? Every time you see energy, you know you need Q. So Q equals MCAT. And I put liquid here because it says water. So we're going to do the mass of the water, multiply it by the specific heat for water, multiplied by the change in temperature of the water. It went from 25 up to 55. That's a change in temperature of 30 degrees. Multiply that together and you get 62,700 joules. That's how much energy the water absorbed from that butane releasing the energy. How many grams of butane did you burn? Well, you started with 8.5 grams, you ended with 7.2 grams, so you burned off 1.3 grams of butane. Next, how many moles is that? Well, we know the formula of butane is C4H10. So we got to add up from the periodic table 4 carbons and 10 hydrogens. That adds up to 58.14 grams in 1 mole of C4H10. So we burned 0.022 moles of butane. So how many kilojoules were released per mole? So we got to take, oops, let's let the computer do its thing. Okay, 62,700 joules from our answer in part A, divided by 1,000 to get it into kilojoules. That's 62.7 kilojoules. That's how much energy was given off for 0.022 moles. Punch that in your calculator and you get 2,850 kilojoules per mole. All right, changing gears. Number 4, draw the energy diagram for a generic exothermic chemical reaction that shows the activation energy and the potential energy of the reactants and products and the heat of reaction. Do the same for an endothermic reaction. Okay, so exothermic, you go up and way down. So I'm going to put my reactants at the start, of course. The energy from the reactants to get to the transition state, the top of the roller coaster, is here. Here are my products. And the heat of the reaction is the difference between, it's like if I drew a little line right here, the difference between the reactants and the products. That's called the heat of reaction, RXN for short, and it's negative when it's an exothermic reaction. That's just the notation. Okay, so now let's do kind of the mirror image here to show an endothermic reaction. Now our reactants are lower in energy than our products. Activation energy is really big for this one. And the difference between the reactants and the products, I'm going to draw it going up this time, it's a positive heat of reaction. Alright, number 5. Using the table above, what's the total energy required to break all the bonds in 1 mole of ethanol? So C2H5OH. Let's see, review your honk 1, 2, 3, 4. It's been a while since you've drawn structures. Okay, how much energy is it going to take to break all of these? Well, first let's figure out how much energy it takes to break the CH bonds. How many are there? I count 1, 2, 3, 4, 5 CH bonds. It takes, according to this chart, 414 kilojoules to break 1 mole's worth of CH bonds. So I'm going to multiply that. It's going to be 2,070 kilojoules per mole. Next, let's do carbon-carbon bonds. There's only one of these that I see, and according to this table, it takes 347 kilojoules per mole. So 347 kilojoules per mole. We've got more bonds to break. Next, let's do the CO, the carbon-oxygen bond. There's one of those. It takes 351 kilojoules per mole. So don't have to punch that one into the calculator. And finally, there's one more bond, an OH bond. According to the chart, it takes 460 kilojoules to break 1 mole's worth of OH bonds. 460 kilojoules per mole. Now I'm going to add all of these together to find out the total energy to break the bonds in 1 mole. It's 3,228 kilojoules per 1 mole. And the question asked how much it takes to break 1 mole, so we can just say 3,228 kilojoules. Alright, what about for a whole entire reaction? The amount of energy released or absorbed overall is what we're going for here. So first we got to write out the reaction for the combustion of C2H6. So we know combustion is always plus O2, and it always makes CO2 and H2O. Now let's use the Cho method. C2, we're going to need 2 C's here. H6, we're going to need a 3 here. That makes 7 oxygens on the right side, because there's 4 here and another 3. So that means I need a decimal here, 3.5. I can't leave it that way. I need to multiply all of my coefficients by 2. So the final answer will be 2, 7, 4, 6 for my coefficients. I'm also going to draw these out. So I'm breaking the bonds in 2 C2H6s. So I'm going to sketch those out so we can really see how many bonds we're breaking here. So here are my 2 C2H6s. We're breaking the bonds of 7 O2 molecules, and O2 molecules have a double bond between the oxygens. We're making 4, I'm going to put a little divider here, we're making 4 carbon dioxides, so really we're making 8 carbons double bonded to an oxygen because there's 2 for each. And we're making 6 H2Os. So we're really making 12 OH bonds. You don't actually have to draw all of these out, but for people who are visual learners, it really helps them see all the bonds that are breaking and forming. Okay, question A. What's the total energy required to break all the bonds in the reactant molecules? So let's remember what the reactants are. Those are the things to the left of the arrow. So let's start with carbon-carbon bonds. Carbon-carbon bonds, there are 2. 1, 2. It takes 347 kilojoules per mole for each one, so I'm going to multiply by 2. That's 694 kilojoules per mole so far. Plus, how many CH bonds do we need to break? I'm going to count them. 1, 2, 3, 4, 5, 6 for each molecule, so that's 12. According to the table, it takes 414 kilojoules per mole for each one, multiplied by 12 of them, that's 4,968 kilojoules per mole. Plus, we got to break these 7 double bonded oxygens. For each of those, it's 498.7 kilojoules per mole times 7. That comes out to be 3,490.9. Now I'm going to add all of these up to get the total amount of energy it took to break those bonds. 9,152.9 kilojoules per mole. All right, now the fun part. How much energy are we going to get back from making the new bonds? So, like I said, for the C double bonded to the oxygen, we're actually making 8 of those, even though we're only making 4 CO2 molecules, because as you can see from my drawing, each CO2 molecule has 2 carbons double bonded to an oxygen. It takes 745 kilojoules per mole for each carbon double bonded to an oxygen, and there's 8 of them. So that comes out to be 5,960 kilojoules per mole, plus how many OH bonds are we making? There are 12 of them, and each takes 460, or each releases 460 kilojoules per mole. That comes out to be 5,520. Add those two numbers together, we're releasing 11,480 kilojoules per mole. Again, I'm getting all these numbers from this table up here. I just didn't scroll back to it. Here's the C double bonded to an O, and here's the OH. Okay? Alright, so now use the values to determine if this was exothermic or endothermic. You always do energy in minus energy out. So you put in 9,152.9 kilojoules per mole to break the bonds, minus the 11,480 that you're getting out, the energy released. That's negative 2,327.1 kilojoules per mole. If it's a negative number, that means energy is being released. So this is an exothermic reaction. Alright, and the last problem is drawing some energy diagrams when you're given some numbers here. So it says reaction A, the activation energy is 100 kilojoules per mole. The heat of reaction is negative 50 kilojoules per mole. If the heat of reaction is negative, that tells you the shape is the exothermic shape. Okay, so from here to the top is 100 kilojoules per mole, because that's the activation energy. From here to here, that's the heat of reaction, that's negative 50 kilojoules per mole. Compare the energy needed to break the bonds and the energy released by making new bonds. Which is greater? Well, remember, the energy to break the bonds is here, and the energy from making new bonds is on the way down. So which is greater? The energy released from making new bonds. Then it says, draw the reverse reaction. Call it reaction B. So here we're just drawing a mirror image. We can actually figure out what the activation energy is. 50 plus 100, the activation energy for the reverse reaction would be 150 kilojoules per mole. And the heat of reaction would be a positive 50 kilojoules per mole, because it's always just the opposite in the other direction. Which reaction is more likely to occur? Well, reaction A requires 100 kilojoules per mole of reactants to get started. Reaction B requires 150. So reaction A is more likely to occur because it's got a smaller activation energy. Alright, hopefully that helps you with getting some studying